In this video, I'd like to talk about the multiple logistic regression model. So we have some event of interest and we wanted to develop a model that predicts the probability of it occurring. For example, we might be interested in anticipating whether or not a customer churns at the end of their contract or doesn't based on their age, the length of time they've been under contract, the number of people in their household, etc. We might be interested in trying to predict the probability that someone donates to a charity based on their age, based on their income, based on their home value. Or we might try to predict the probability that someone clicks on an ad based on the location of the ad on the website, the color of the ad, the words that are used. So what we'll discuss is how we add in multiple predictors when we're trying to develop a model that predicts a probability, how we incorporate categorical variables, how we incorporate interaction variables, so on and so forth. And I'd like to do this in the context of a real-world example taken from the travel industry. So let's imagine that we are a reservation specialist and we're interested in studying the probability that a person is going to cancel their hotel booking. Now, this is important because every time a customer cancels a reservation, the hotel potentially loses money. If they cancel at the last minute, the hotel might not be able to find another guest and so just loses out on that night's income. Or if the hotel's been fully booked for a long time and a customer ends up canceling, well, who knows how many reservations the hotel missed out on when they went to the website and saw that, nope, there's no availability. So let's load in some data here. So loading in the data, we find that we have information on 480 bookings of some hotel chain located in Portugal. So what do we have about these different bookings? Well, the first column is status, and lets us know if the reservation was kept or if it was ultimately canceled. Now, canceled comes last alphabetically, so our model will be predicting the probability that a booking is indeed canceled. Now, the other columns let us know things like the location of a hotel, whether if it's in the city or if it's at a resort. We have the lead time, the number of days in advance of the arrival date that the customer made the booking. We have the number of nights of the stay, where the customer was coming from, the type of room booked, the number of changes they made to their booking, like changing the room type or something. We know the average daily rate of the booking. Did they pay $50, $100, etc.? And the number of special requests the customer had. Maybe they needed to have a bottle of champagne be left because it's their honeymoon. We also know the number of people listed on the reservation, and then finally the meal plan. Is it an all-inclusive package? Is breakfast included, breakfast and dinner, etc.? So let's review simple logistic regression where we predict the cancellation probability from just a single predictor. Now, how about lead time, the number of days in advance that the customer made the booking? Throwing it through GLM, just doing status twiddle lead time, data equals hotel, adding in family equal binomial to turn on logistic regression, then getting a summary, we see that the coefficient of lead time is positive. Now, in logistic regression, we don't really interpret the size of the coefficient. Instead, we just focus in on the sign. Since the coefficient is positive, we know that reservations with longer lead times have a higher probability of being canceled. By how much more? Well, it depends. It's not a set amount like in linear regression. If we visualize the model, we see it's a slow but steady increase from about 20% for same-day reservations to nearly 80% for reservations made a year and a half in advance. Now, you might remember that our model uses a logistic S-shaped curve to capture the variation in the probability, but this plot looks like the probability is almost linear. Well, if we zoom out a bit, we're able to see that the curve as a whole does indeed have that S shape. It's just that in the values of lead time in the data, it just was a small fragment of that. What if we wanted to use a categorical predictor to predict the cancellation probability? Well, we need to get it into numerical form, and to do that, we represent it as a set of indicator variables. Just like in multiple linear regression, if our predictor has L levels, we're going to need L-1 indicator variables to represent it. Now, the level that comes first alphabetically, we call the reference level. That doesn't get an indicator variable named after it, but every other level does. That is going to equal 1 when the booking has that level, and 0 otherwise. So let's predict the probability of canceling from whether or not the person is a repeat guest or not. The levels are yes and no. No is going to be the reference level, so our indicator variable will equal 1 when the person is a repeat guest and 0 if not. So we'll use the formula status twiddle repeat guest, and we find that R has made the indicator variable repeat guest yes. So remember, it's taken the column name and appended the level for which this variable equals 1. And we see that the coefficient is negative. So that lets us know that the probability of canceling for repeat guests is lower than the probability of canceling for new guests. However, since the p-value is bigger than 0.05, the difference in probability is not statistically significant. Our data can't discern a difference in probabilities of cancellation if you're new versus repeat. Now, how does the cancellation rate vary depending on the guest's country of origin? Well, we can do status twiddle country, and we see that R is defined 3 indicator variables. So England is the reference level, we have France, Portugal, and other, and looking at the coefficient of Portugal, we see it's positive. So what does that tell us? Well, something pretty specific here. So the cancellation rate for Portugal is higher than the cancellation rate for England, our reference level. The difference is statistically significant. The p-value is less than 0.05, but that's not really an insight that we care about. Normally we care about whether there's any difference in probabilities across all the levels, and for that we need the drop one command. So when we run drop one, we're going to add the additional argument test equals CHISQ instead of test equals F, which is what we use for multiple linear regression, because it's a slightly different sort of test in order to determine if that variable is statistically significant. So we see that the p-value of country is less than 0.05, so yes, country is a statistically significant predictor of the cancellation rate, and the implication of that is that there's some difference in cancellation rates across the 4 levels of country. Now, the test doesn't tell us which countries are different, but it does at least let us know that they're not all the same. All right, so let's add more than one predictor into the model, and we'll do this in the same way that we did with multiple linear regression. Let's not consider interactions just yet, so we can simply twiddle dot our formula to use all the predictors that we have access to. So if we wanted to use a subset, we could just use the column name, separate them by plus signs, but let's just twiddle dot it and predict the status of the reservation from all the predictors in the data. Now, my favorite thing to do is first to check the results of drop one. Since often we're going to have categorical variables with many levels, that's really the only way to know if those variables are statistically significant. So running drop one and scanning down the list, we find that lead time is statistically significant. Length of stay, country, room type, they're all significant since their p-values are less than 0.05. However, month, people, meal plan, not statistically significant since their p-values are greater than 0.05. So what does this tell us? Well, it tells us something really specific, just like it did for multiple linear regression. For example, lead time, which is statistically significant. Being statistically significant tells us that if we started with a model with the other predictors in it and then added lead time to it, we'd get a statistically significant reduction in the deviance of the logistic regression model. Now, what's the deviance? Well, it's complicated, but we can think of it as a type of error made by the model. Lower deviance means we're closer to a perfect fitting model, a lower error overall. So, in other words, adding lead time to a model that already contains the other predictors improves the predictive power of the model. And yet another way to think about it is that the lead time contains additional information about the probability of cancellation of a booking above and beyond the information provided already by the other predictors in the model, the length of day, the daily rate, room type, etc. Now, meal plan we see is not statistically significant. So this means that adding it to a model with the other predictors already in it doesn't really reduce its error by more than what adding in some unrelated random predictor would do. So in other words, meal plan doesn't add any new information about cancellation rate above and beyond what the information contained in the other predictors contain, the lead time, the length of stay, room type, etc. Now, just like in multiple linear regression, the p-values of a logistic regression model are model dependent since they're a comment on whether the predictor adds new information above and beyond what the other predictors offer. So to see this in action, consider predicting the probability of canceling based on just meal plan. Fitting the simple logistic regression and running it through drop one, we find the p-value to be less than 0.05. So by itself, meal plan is a statistically significant predictor of the cancellation probability. It does contain information as to whether someone is or isn't going to cancel, but we did see it was not significant in the full model. So this tells us that the information that meal plan provides about the cancellation probability is redundant with the information contained in the other predictors. It's not offering anything new above and beyond the information provided by the other predictors in the model. Let's also consider the price someone is paying for their booking. In a simple logistic regression predicting the status of the reservation from the daily rate, we find that by itself, it's not a statistically significant predictor of the cancellation rate. Its p-value is above 0.05. However, it is statistically significant in the full model. So the relationship in the simple logistic regression must have been just getting washed out by the variation in the probabilities due to other factors. But once we account for them, the daily rate does have something to say about the cancellation rate of bookings. All right, so let's talk about these coefficients. And once again, we're not going to worry about the sizes of the coefficients, only their sign. So let's look at the coefficient of lead time, which is positive. Now, what does this tell us? This lets us know that when we compare otherwise identical bookings, so same location, same month, same length of stay, same room type, same daily rate, etc., the booking with the longer lead time has a higher cancellation rate. Now, the coefficient doesn't tell us how much higher, since that actually depends on the difference in the lead times. We need to run our model through the predict function to get concrete numbers. Now, if we look at the coefficient of the total number of special requests, we see that it's negative. So this lets us know that when we compare otherwise identical bookings, same location, same lead time, same month, same length of stay, same room type, same daily rate, etc., the one with more special requests has the lower probability of being canceled. How about room? Well, the coefficient of the indicator variables aren't going to tell us much here. The coefficient of room C is negative, so this lets us know that when we compare otherwise identical bookings, same location, same lead time, same number of special requests, etc., the booking for room type C's have a lower cancellation rate than the bookings for room type A. Now, if we wanted to know a different set of rooms like C versus D, which one has the higher cancellation rate, we can subtract the coefficients. So D minus C works out to be about positive 0.9. So among otherwise identical bookings, room D has the higher cancellation rate. Now, there's really only so much we can do by looking at the output of summary. Instead, I'd recommend, whenever possible, taking a more visual approach to understanding the implications of a multiple logistic regression model. Now, unfortunately for that, we can only look at one or two variables at a time, but let's see how that goes. First, what happens when we use a categorical predictor in our model? Well, in a linear regression model, we saw that adding a categorical predictor gives each level its own regression line. Now, they all have the same slope, but they're just shifted up and down from one another. They have different intercepts. For example, imagine we predicted the lead time from the daily rate and country of origin. Running that model through Visualize Model, we see that the lines relating lead time to daily rate are all parallel. They have the same negative slope, but England is shifted up above the others with Portugal down at the bottom. The vertical separations tell us the difference in the average lead time when we compare reservations across different countries for rooms at the same daily rate. So for people from England, well, they have the highest average lead time after accounting for the booking's daily rate. Now, in a logistic regression model, something a little bit different happens. Each level will get its own logistic curve. These curves will look the same, they'll just be shifted left to right. And the implication of this is that one curve will always be higher than another or always below one another. So let's see what happens when we try to predict a booking status from its lead time and location, the city versus resort location here. So we see that at all lead times, the cancellation rate for city hotels is larger than for resorts. And zooming out a bit just to see the full curve, we actually do see that it's the same curve, the same S shape, it's just shifted left to right. Well, what about meal plan? If we predict the cancellation rate from the lead time and meal plan, we see that all inclusive has the higher cancellation rate at every lead time. Zooming out, we see each curve has the same S shape, it's the same curve, they're just being shifted left and right. All inclusive always has the highest probability of cancellation, while none always has the lowest probability. Now, what if we do have the variables interact? Well, remember that in a multiple linear regression, when a numeric and categorical predictor interact, each level now gets its own line and they're allowed to have different slopes and different intercepts. For instance, we could predict the lead time from the length of stay and the location of a hotel, allowing them to interact by separating the columns by a multiplication symbol in the formula. And when we set that up, when we visualize the model, we see that city and resort hotels get their own lines. The strength of the relationship between lead time and length of stay is much stronger for resort hotels than it is for city hotels. but something more interesting is going on, I think. If we compare reservations with short lengths of stay, like 1 to 2 days, the average lead time for city hotels is higher than the average lead time for resorts. But the opposite is true once we look at longer stays. For stays near 10 days, the lead time for resorts is higher than for city hotels. Now, in a logistic regression, when we have an interaction with a categorical predictor, each level is still going to get its own logistic curve, but now those curves are allowed to look different. The levels can have different shapes, different strengths in the relationships, and can sometimes even have different directions. Let's go ahead and predict the probability that a booking is canceled from its lead time and the country of origin, allowing those two predictors to interact. And cool! The relationship for Portugal is strong and positive. Bookings from there always have the highest probability of being canceled. The relationship for other countries is still positive, but it's much weaker than for Portugal, since the increase in probability isn't as fast. But look at England. Its relationship is weak, but negative. For England, bookings with longer lead times tend to get canceled less often. Comparing France and England is interesting too. For small lead times, England's cancellation rate is higher than France's, but at longer lead times, France's cancellation rate is higher. Zooming out, we do see that each curve is the characteristic S-curve, but they vary in S-ness, in its strength. Some increase relatively quickly with lead time, like Portugal and France, others more slowly, like the other countries, and England's is negative. Let's look at another. How does the probability of cancellation vary with daily rate and whether someone is a repeat guest? Throwing in the interaction and visualizing the model, wow, that's really quite peculiar. The probability of canceling is super steep, right below $200 for a repeat guest, but it only slowly increases for new guests. It's almost like there's a rule saying, hey, if the price is above $180 and the guest is a repeat, they're almost always going to cancel. All right, so what else do we need to know about? How about when we want two numerical predictors? In multiple linear regression, when we predict from two numerical quantities, like predicting lead time from length of day and daily rate, the relationship between lead time and length of stay is going to have the same strength, regardless of daily rate, and vice versa, as long as we don't include an interaction. So fitting this model by separating those columns with a plus sign in the formula, then visualizing it, we see that regardless of whether the length of stay is small, medium, or large, the relationship between lead time and daily rate is strong and negative, with always the same strength. Further, the differences in the average lead time between long and short lengths of stay, when we consider bookings at different daily rates, it remains the same. When the daily rate is about $50, the difference in average lead times between long and short stays is just under $40. Same difference if we compare bookings whose daily rates are $150. Now, if we allow these variables to interact, well, the strength of the relationship between lead time and daily rate is now allowed to vary based on what kinds of length of stay we're looking at. Fitting this model by separating the columns with a multiplication sign now in the formula, then visualizing it, we see that while the strength of the relationship between lead time and daily rate is negative, regardless of the length of stay of the booking, sometimes it's stronger and sometimes it's weaker. When the length of stay is large, the red line, the relationship is fairly weak. For short lengths of stay, the blue line, the relationship is really quite strong. Also, if we look at the differences in the average lead times between long and short lengths, the size of the difference depends on the daily rate. For $50 daily rates, the difference in average lead times between long and short stays is about 20, but for $150, the $150 daily rates, that difference is much larger, around 80. So what happens when we have two numericals in a logistic regression? Well, when the two numeric predictors don't interact, and we just separate those columns by a plus sign in the formula, we get curves that have the same shape, implying the relationships have the same strength, they're just shifted left to right. So let's try predicting the status of a booking based on its lead time and on its daily rate. So fitting the model, visualizing it, well, it looks like we need to zoom out to really see the curves, and doing so, we see the relationship between the probability of canceling and the daily rate looks to be the same, except for a horizontal shift whose size depends on the lead time. The curve for large lead times is shifted to the left, the curve for small lead times is being shifted to the right. The net effect is that regardless of the daily rate, the cancellation probability for large lead times is always higher than it is for short lead times, but the strengths of the relationship is the same. With an interaction, that story can change. Let's try predicting the status of the reservation based on the length of stay, its lead time, and the interaction. So separating the predictors by a multiplication symbol in the formula and visualizing it, well, wow, what a story here. First, let's look at the relationship between the cancellation rate and the lead time. For small lead time, last-minute bookings with a long length of stay, well, those have a higher cancellation rate than bookings with short stays. But this flips for longer lead time reservations. When the lead time is a couple hundred days, now short stay bookings have a much higher probability of being canceled than long stay bookings. The shape of the S-curves look very different between long and short stay bookings, indicating that the strength of the relationship between canceling and lead time depends quite strongly on the length of stay of that booking. But the plot thickens. If we look at the relationship between canceling and the length of stay, the relationship is negative for bookings with large lead times. For bookings made well in advance, the longer the stay, the less likely it is to get canceled. But when the lead time is short and it's a last-minute reservation, the longer the intended stay, the higher the chance it will be canceled. The whole direction of the relationship between canceling and the length of stay changes sign depending on the lead time. And there's more to the story too. If we look at short stay bookings, those made well in advance have a much higher probability of being canceled than last-minute bookings. But if we look at long stay bookings, those made well in advance have a much lower probability of being canceled than last-minute bookings. So there we have it. In multiple linear regression, when two numeric predictors don't interact, the line describing the relationship between y and x1 stays the same strength. It just shifts up and down depending on what value of x2 that we're looking at. Now, when they do interact, though, the line describing that relationship between y and x1 kind of shifts around, having a different intercept and a different slope depending on what x2 is. The interaction really is a great way to add flexibility to the model and to capture additional realism when the strengths of the relationships are expected to vary based on characteristics of the individual. Now, in a multiple logistic regression, when two numeric predictors don't interact, the curve describing the relationship between the probability of our event and x1 always is going to have the same S shape. It just shifts left and right depending on the value of x2. But when they do interact, the curve describing the relationship between y and x1 can have really different shapes depending on what x2 is. Sometimes the curve increases quickly with x1. Sometimes the curve increases slowly. In fact, the whole direction of the curve can change too, from increasing with x1 to decreasing with x1. Just like in multiple linear regression, the interaction is a great way to add flexibility to the model and capture additional realism if the form of the relationships are supposed to be highly dependent based on the characteristics of the individuals that we're studying. Now, when it comes to interpreting the coefficients of a multiple logistic regression model, just remember to basically ignore the values of those coefficients and just focus on the signs to broadly understand how the relationship between the probability and the predictor works. And if at all possible, make a visualization to better understand your model. As they say, a picture is worth 1,000 words. And also, 2 Frenchies are worth 1,000 models. Here's Jackson.